Hartshorne. I'm going to be presenting on my research on effective grain boundary engineering and grain boundary engineered microstructures on 316L stainless steel.
Now you're going to talk.
Is that going to be an issue?
Well, I mean, it's registering, and I have up to the highest level. I mean,
Yeah, the problem is the AC, right?
Yeah. I can adjust the control level.
Hold on. Is this any better? Test 1, 2,
Yeah.
Matthew Hartshorne. Okay. Just leave it like that, maybe? It's streaming. Yep.
Right.
Or it says it is. Nice.
She loves to play that now.
Nice. Please, copy me. No, he just did. Like just now. Oh yeah. I'm gonna make a PowerPoint presentation. He's gonna send me his, and like I already have mine. Right. Oh yeah. Like I.
CRF is and I said it's like a cancer to productivity for grad students. It takes people's ability to complete work and it rips it to shreds.
Yeah. Well, for your stuff,
Some
absolutely.
Some instruments.
I mean, the problem is we need 2 more XRDs.
Which was something I complained about.
Yeah.
Even though I don't use it.
I mean, like it gets booked constantly, so we need at least 1 more system probably.
I told them it's essential to my work and I can't get it on the system.
Describing the CRF as a property.
Looks good, man.
See how this goes.
Sure, whatever.
One way or another.
Get nihilistic stuff.
I've been there for like 9 months. Ever since the pre-defense. Yeah, feel free to just turn that thing off.
It's really hot.
Yeah. I'm going to sweatsuit as everyone else. Yeah, I mean, it's Rex's.
I think that the
car.
American unit right outside the window.
Yeah. Unless I delete it. Yeah. Dr. Lamerson? Are you there?
Good to see you.
I have a hard copy of that dissertation.
Oh, fantastic. I will take it.
I will stick it in your mailbox in MEM.
Whatever happened to that paper? That's from 2 years ago.
Yeah, that one.
Right.
That I do not have.
I'm here, don't hear. Is the camera stuff set up?
Ish. Probably. Yes. Tucker.
That's why I'm sitting here. Good luck. You gotta sit in the same spot.
Well, if we're doing the same spots, Wayne, get up here. I'm going to sit there. Yeah, right?
I feel like anytime I get specific, somebody would go, that's
Don't worry, I'm sure that will happen today.
Thank you.
That's what ended up being this morning. I was like starting to projects. I'm like, I'm should change anything right now. Yeah, it used to be one was in the air. Yeah.
Well, this looks nice. Not so much that.
That's okay about the little change. I mean, if you want to get rid of that, sure. Really don't care.
I didn't tip it because I didn't know if I should.
See, I didn't wait. That's true. Ready. I'll cover each of them.
Take one for the team.
That's right.
Okay, I just want to ask because you know I want to be like that person. Cheers. None of them work either. They're all like this, or you're looking a hole. It's on my
Hey Chad, it's Matt. How are you doing?
Good.
Can you hear me okay?
Yes, I can.
Okay. We're still waiting for everyone to show up. I want to get you on the line sooner rather than later.
Yeah, sounds good.
Yeah, I'm at 70 something. Practice yesterday came in at 52 minutes, so it's longer than I wanted.
About 20 minutes too long.
Yeah, it's 20 minutes longer than I wanted. Of actual work that like is shown in the presentation, 2.
Well, I think that's
Mitra will be here shortly. Roger. According to an email at 9:16 last night, he is looking forward to it. He is coming, and he has edits. What? That's probably a good idea. We're missing him too. The chat's on the phone. He's sorry, what? Yes. I have forms up here. Okay. Did she send you out? Good morning. I should know. I emailed everyone with reminders, not just you. Sorry about the confusion yesterday. Apparently.
You've just been here for 10 years.
12.
That's true. Wait a second, yeah, because I've been here for
Yeah.
9 years.
Uh-huh.
You're so old, Matt.
Yes.
Okay. Who do you have? You have Chad.
Everyone's here now.
Skype?
Chad's on,
Okay.
he's he's on speakerphone.
Okay, hi Chad. Hi, thanks for joining us. And everybody else. We're good?
Leslie. Dr.
Yeah, I
Tucker.
see that.
Okay, Roger. Everyone's here.
Oh, you made it. Wait. Is that everything? Where's that?
Behind Roger. Yes. Go ahead. Let's go. Oh, your slides are here.
Let me get my unhealthy snack.
Okay.
I decided to like be healthy after all of your defenses. Let me enjoy this time.
Okay. I brought bagels.
They're really no healthier than that.
No, but they taste like they're healthier.
They do.
Joe, can you time me? Thank you. Whether what? Oh.
See, I'm feeling better.
Hmm?
Maybe have the ocean.
Oh. Yes, exactly. Sprinkling stuff on top that looks healthy makes it healthy.
Okay. Thank you everybody for coming. Asher. Can't shape up, you gotta ship out. Alright, so thanks everybody for the culmination of Matt's large portion of your academic life.
Yes.
Starting. Matt's been a great member of our group for a long time, and I think I hope you guys enjoy his thesis and showing all of his wonderful contributions to the group. And so again, just for the purposes of Chad and everyone else, this is going to be a presentation of Matt's PhD thesis, followed by open questions from the audience, and then we'll have a closed question and answer session just for the committee for Matt. Okay? All right. Thanks.
Thank you all for coming. I'm going to be presenting on my research on the effect of grain boundary character and grain boundary engineering microstructures on the sensitization and corrosion of 316L. Here's a brief outline. Going to go through the motivation background. I have my results broken up. First, how we calculate the grain boundary plane, then how we generated our GBE structure, how we characterize that, correlated corrosion with TM, and then the bulk corrosion properties. Before quick conclusions, future work, and then the Spanish Inquisition. So first, why do we care? Corrosion is incredibly costly to the economy. $276 billion a year, according to NACE. It's about 3% of GDP for the U.S. and almost $1,000 per person per year. There are
I'm sorry to interrupt. Can you just stand just a little closer to the microphone? Just your positioning a little bit.
Can you hear me now?
The interruption. And then if you could just say when you
Slide numbers?
Slides.
Got it. I'm on slide 3 right now. Can you hear me any better?
Yeah, that's great. Thanks.
Okay. There are a number of different mitigation strategies. First is coatings. However, with these, you have to maintain that barrier. Second is cathodic protection, and there you have either the power draw from active systems, or you have to continuously replace the anodes for passive systems. And finally, you can use inherently more corrosion-resistant alloy. Slide 4, Chad. So, question is, how can these alloys be modified to actually prevent corrosion? This was first done in about 1913 by Harry Brewerly at Brown Frith Labs, and he noticed that his samples that he had added chrome to when he was making knife steel had actually significantly resisted etching, and the composition that this happened with was 12.8% chromium and 0.24 weight percent carbon. But what they found afterwards is that any alloy containing over about 12% chromium resists corrosion quite well, and also frequently added are nickel, molybdenum, copper, niobium, and titanium. So what actually happens is the chromium is added to form a passive layer. When it encounters oxygen in an environment, it forms a very thin layer of chromium oxide. This is impermeable to oxygen, unlike the iron oxides that form, so that it prevents further attack by oxygen. Nickel is added to stabilize the SAC structure instead of the normal BCC structure at room temperature, and this increases the ductility, toughness, and workability. The sample composition, or the composition range for 316 is shown below, and the big thing to note here is it's 16 to 18% chromium, 2 to 3% molybdenum, which is different than 304. That doesn't have any molybdenum in it, and nickel is 10 to 14%. Note that the 14% is the upper limit of this range, which will be important later. So the problem with this stainless steel is that when it's heated into the 400 to 750 Celsius range, you get precipitation of M23C6 carbides. First you get the interstitial segregation, primarily carbon to the grain boundaries, The chromium follows it, and you end up with these carbides precipitating there, which is shown in an energy filtered TEM image on the right. So in this particular image, since it's energy filtered, the brighter it is, the more chromium it has. So, Chad, this is slide 7. So here in the center, you have the M23C6 carbides, where M is either iron or chromium, but primarily chromium, as you can see here. And then you have this kind of neutral gray for your matrix, and then you can see it's darker immediately around those carbides, which is because the chromium there is depleted. It's been sucked into the carbide. The problem with this is that it can drop it below 12%, so you change the oxide structure back to the normal iron oxide structure, and it's no longer permeable to oxygen, or impermeable to oxygen. But the real problem with this is that you now have a galvanic couple between your very large grain area with the passive layer and a very which is a large cathode, and then a very small anode area around the grain boundaries, which is vulnerable, so you get very aggressive attack there. Slide 8. You can get a couple different kinds of attack. The most commonly studied is intergranular corrosion, and that's shown on the right here. And this is chemical attack of the grain boundaries, and it's usually assessed with the ferric sulfate sulfuric acid test. This is a very set chemistry of the set amount of ferric sulfate, sulfuric acid, and water, and it's boiled inside a flask with a condenser. And the point of this is that you actually get it's very reproducible across different laboratories. However, you also have a second kind of attack called intergranular stress corrosion cracking. And this is, in addition to the chemical component, has a mechanical component as well. And it's experienced more in surface conditions. And the big thing with this is you can actually get it at lower sensitization levels than you can get the intergranular corrosion. And this is typically studied with a U-bend test or a slow strain rate tensile. And the catch with this is, especially with the slow strain rate tensile, you need a through thickness microstructure to study it because it's machined from the bulk alloy. Slide 9, Chad. So the question is, we see the grain boundaries are being attacked, and we want to know what's different about the different types of grain boundaries, and first we have to know how to describe them. There's 5 macroscopic parameters and 3 microscopic parameters. The macroscopic parameters is again divided up. You have your grain orientation, so each grain is its own crystal, and those crystals can be tilted in 2 axes relative to each other, and they can also have a twist. And then the grain boundary plane, where those 2 crystals actually meet up, can also be tilted in 2 different axes. The microscopic parameters are small translations in 3 dimensions that are a fraction of the unit cell. So now that we know how to describe them, the grain boundaries can be classified. First is the low angle grain boundaries. This is less than a 15% approximately grain boundary, or the angle between the 2 grains. And this is typically described as a network of dislocations, and it's shown in the top image on the right. So we have on the left 1 grain, on the right another one, and right in between you can see these dislocations that are required to make the 2 crystals match. And this is the spacing of the dislocations is described by this relationship here, which we have the spacing, the Burgers vector of the dislocations, and the actual angle of the 2 crystals. If you have a larger than 15 degree misorientation, you have what's termed a high angle grain boundary, and there you typically have a much poorer fit, and that's shown in the bottom image. It doesn't line up as nicely as it does in the top. And this causes much more free volume and free energy, which can be seen as the white space. Slide 11, Chad. A specific subset of the high angle grain boundaries is the coincident site lattice boundaries. And this is at specific tilts and twists, atom positions in the 2 grains will line up. So in the figure, we have our red crystal and our blue crystal, and when you lay them over top, the yellow dots in the bottom image correspond to sites that are actually shared between the 2. And this was described by Ranganath. He came up with equations to calculate the fractions, the fraction of coincident sites, and that is typically denoted by its sigma number, which is the inverse of the fraction of coincident sites. So if 1/3 of the sites are shared, then it would be a sigma 3 grain boundary. So these are special because they can have lower grain boundary energy. A plot of boundary energy with respect to misorientation angle is shown on the right. And you can see as you move away from 0, your energy rapidly increases here. However, at specific tilts, you have cusps. And you can see that these are denoted by the sigmas. Again, not all of them are the same. Even for the same sigma number, you can see that there's a small cusp for the sigma 3, and then a much deeper cusp for the sigma 3. And this is related to the grain boundary plane. So the sigma notation just tells you how the two lattices are related. It doesn't talk about that grain boundary plane at all. And depending on how the two crystals meet up, that will determine how many of those coincident sites are actually on that grain boundary plane. And the deepest cusp there for the sigma 3, as you can see at the top there, terminates on the 111 plane. So, slide 13, Chad. Moving on to the grain boundary engineering, Watanabe proposed in 1984 that these grain boundaries could be used to improve the properties of polycrystals by processing the polycrystals so that you have more of them. Typically, more of the low CSL, less than or equal to 29, sigma less than or equal to 29. And the idea was this way you can adjust the properties, including the strength, ductility, and corrosion resistance. And the way that you get more of these CSLs is through thermomechanical processing. And that's generally broken into two subsets for grain boundary engineering. You have strain annealing, where you put in a relatively small amount of strain and heat it at a low temperature for a long period of time. This is typically a single-step process, but there are multi-step processes that exist. And then there's also recrystallization annealing, where you put in more strain, 5 to 30%, heat it at a higher temperature for a much shorter period of time, and then iterate this, generally 3 to 7 times. So this has been shown to be successfully applied in service conditions. On the right are shown lead. These are lead acid battery electrodes, and they put in over 50% CSLs and were able to significantly reduce both the weight loss and the grid growth. And then in another study in pure nickel, they were looking at the creep rate. They went from a 13% to 66% CSLs and now had 1/16 of the creep rate and completely eliminated cavitation. Now, in stainless steel, the results have been a little bit more mixed. In this case, in stainless steel, we're mostly concerned about the corrosion resistance instead of the creep rate. However, on the left here, this is work by Dr. Christopher Barr here at Drexel. The two arrows denote sigma 9 grain boundaries, and you can see the one on the left did not corrode, the one on the right did. And they have the same misorientation because they're sigma 9s. However, they probably have a different grain boundary plane because of different corrosion resistance. Conversely, in Hu's work on the right, in a similar type of test, he found that only the sigma 3 coherent twins were resistant to corrosion. Slide 16, Chad. This is some of my initial work, and the EBSD map on the right shows this sigma 3 in red. You can see that it's actually curved, and in the zoomed in SEM image on the left, you can see that you have no corrosion attack on some of the straight sections. Some of the straight sections are corroded, and then we have this curved section that was corroded as well. So because the grain boundary trace is varying, this indicates that the grain boundary plane is also probably varying. But one of the questions is how can we relate this to the bulk corrosion properties? And Dr. Jones and Dr. Randall had suggested a way that we could do this, because they noticed that using two different strain annealing procedures, they actually ended up with somewhat different microstructures. They used a tensile GBE shown in the center and a cold rolled GBE shown on the right. And this is from a stereological analysis method. And what it is statistically looking at the microstructure from a very large number of grain boundary segments. So the values are shown in multiples of random distribution, or MRD. So the higher it is, the above 1, the greater the deviation from what you'd expect from a random distribution. And what you can see is that when all grain boundaries are taken into account around the 111 pole here, it's about 3.56 for the as received. For the tensile, it's actually dropped, and this indicates that the level of coherence of the twins present has actually dropped, and you can see that there's greater spread in this microstructure as well. And then in the cold rolled, it's actually increased above the annealed. So by using these two processing routes, you can actually compare the coherence. And in the 60-degree rotation about 111, we see the same sort of trend. And there's slightly different grain growth as well. But that brings us to some of our questions. How does the grain boundary plane play a role in the corrosion resistance in stainless steel? It looks like it does, but we're not quite sure how. And how do corrosion-resistant grain boundaries affect the bulk corrosion resistance of the material? So, moving to our experimental approach, Chad, this is now slide 20. I used a multi-scale approach, starting on the macro scale using ASTM corrosion techniques, primarily the A262 practice B mass loss for the intergranular corrosion and the G123 for U-bend for the intergranular stress corrosion cracking. At the mesoscale, I used primarily EBSD analysis and also correlated EBSD and corrosion. And then on the microscale, I used transmission electron microscopy and electron energy loss spectroscopy coupled with that, as well as automated crystallographic orientation mapping, which I'll be referring to as ACOM. The material that we used was primarily 316L Biodor provided by Carpenter Technology Corporation. 316L is widely used, and it's more corrosion resistant than 304. It has a slightly higher alloy content. Compared to the 304, the moly's been added, but in this heat specifically, the nickel's actually even a bit above spec. It's 14.73%, and typically it's not above 14, and in a lot of heats it's down in the 10 to 11 range. So moving on to my results. First question was calculating the grain boundary plane. There are established methods for doing this in TEM, but initially we wanted to do atom probe tomography and correlate that with the grain boundary plane. However, the problem with that is the specimens for that don't load it well into a standard double tilt holder. We do have a dedicated holder for them for TEM. However, it's only has a single rotation axis, which makes typical analysis somewhat more difficult. However, we do have our ACOM system. So what we can do is we tilted the grain boundary so that it's parallel to the beam. And that angle is then beta. In this case, it's 0 because it's parallel, but if you know your angle, or if you know your thickness and you can measure the width, you can calculate that. Then you also measure this alpha between the grain boundary and the x-axis. And then you vectorize those in vector A and B, and the cross product of those is your grain boundary normal. And if you multiply the orientation of either grain by that normal, you end up with your the local crystallographic faces of those grain boundary planes. We tried this on a coherent sigma 3, and we're within 3 degrees, which is getting close to how closely we could align that grain boundary. And I have the reference here for Dr. Randall's paper. She had discussed how to do this in SEM techniques, but we realized we could apply this to TEM, and then Asher Leff helped me write the MATLAB code for this. So moving on, we wanted to see how we could apply this to other materials as well, especially atom probe specimens. This is what's shown is a 5456 specimen, and the on the left we can see the grain boundary has been decorated by these precipitates, and by getting ACOM scan, we can then calculate the local grain boundary planes for each of the grain boundary segments between those precipitates. So moving on, we're on slide 25 now, Chad. Next question was propagating our GBE microstructure through thickness. Most of the work in GBE has looked at the rolled surface because that's the most affected region. However, for the slow strain rate tensile specimens, we wanted to be able to machine samples out, and this also has industrial applications because you can then machine bolts and things like that. So Dr. Barr's procedure that he spent quite a bit of her time refining, he settled on a 5% rolling reduction and then a 1 hour hold at 1000 Celsius. However, he did not look at the center line. Michucci used a very similar procedure, except that he held for 72 hours. And he reported that he was able to, by doing that, propagate through the thickness. And again, we wanted that for the best corrosion performance. However, when we attempted his procedure, we found that it was significantly more variable than we would have liked. The grain boundary maps are shown in the top, but the big thing is our sigma 3 to the n, which when I say that here, it's the sigma 3, sigma 9, and sigma 27s added together. The total fraction in the left map was 72%, which is pretty good, but it was only 50% in the right map, which is much more indicative of the length fraction expected for a annealed microstructure. So that is referred to here as the SR condition. We went back and we tried several iterated procedures. Again, we're still using 5%, but we tried 3 iterations and then 1000 and 1020 Celsius. And we tried different times as well. And what we found was here, our sigma 3 to the n content was rapidly reached a relatively high level and was highly consistent, using 2 hours at 1020 C, repeated 3 times with 5% strain. So moving on, Chad.
The two colours are the two different section surface on it. That's previous slide. The blue and the red are surface and center.
No, the red is 1000 Celsius,
Okay.
and then the blue is 1020 Celsius. And they're also using a slightly different
So
times
they're all
as well.
measured at the center.
They are all measured at the center. Chad, we're on 30 now. We're moving on to our microstructural characterization. So we have our annealed microstructure, which is our control. That's what was delivered to us and then briefly annealed to remove the cold rolling. We have a rolled GBE, which I just talked about, and then we have a tensile GBE procedure that was published by Dr. Jones and Dr. Randall. And the most reported metric for GBE at this point is the length fraction. However, there's several different ways to classify that. The most traditional is the Brandon, that's represented here by the B. And then there's also the Plumbo-Aust criterion, which is a little bit tighter, and that's been shown to track a little bit better with corrosion performance. Then there's also just a flat 2-degree cutoff. And that's actually much tighter for sigma 3s and a little bit looser for the higher order sigma grain boundaries. And what we found was that the rolled GBE has slightly higher content than the tensile GBE, and the annealed is about 20% lower in length fraction compared to the GBE. But the really big difference that kind of surprised me with this was the length fraction of sigma 3s under the 2-degree criterion, 61% for the rolled GBE, and it's down to 53% for the tensile GBE. And what this denotes is that in the tensile GBE, the sigma 3s are actually more highly deviated from the ideal. They're still within the criterion for the Brandon criterion, but there's a significant percentage of them that are beyond 2 degrees. Moving on to the stereological analysis, we were somewhat surprised to find that we actually had the same number of grains terminating on 111 in all 3 microstructures. This is not what was shown by Dr. Jones. And when we look at the 6 degree about 111, we actually have a much higher fraction of sigma 3 segments noted by the about 2,800 MRD compared to his reported about it in the range of 1,000. But again, they're the same across all three microstructures, which is not what he showed. There was a follow-on work by Randall where they noted something similar in only the tensile, where when they iterated it, they saw that it again returned closer to what the annealed was, but they didn't see, it still wasn't quite identical, and they didn't look at the rolled condition. When we move to the triple junction analysis, when three grain boundaries meet, you have a triple junction, and we're looking at the number of CSL grain boundaries that meet there. So a 3 CSL grain boundary has 3 CSLs all meeting. And generally, those are considered to be immune to corrosion. And what we found was that the tensile GB had more of these 3 CSLs and also had fewer of the 0 CSLs, which is important because 0 CSLs, if you have a high angle grain boundary with a crack propagating along it, hits a triple point with 2 other high angle grain boundaries, actually multiplies, so you end up with 2 other cracks propagating, or it can do so. The 2 CSL, on the other hand, was higher in the tensile GB. This is important because the 2 CSL can actually theoretically arrest cracks. So if you have one traveling along and that runs into a triple junction with 2 CSLs, it can stop. However, this trend does reverse if we only consider the sigma 3s to be special, and then the rolled is more likely to arrest cracks as well. Next metric is grain size, which is a deceptively complex question in this. On the left, we're considering all grain boundaries, and on the right, we're excluding sigma 3 to the n. And the idea there is to get at what's called a twin-related domain. So the idea there is you can get inside a twin-related domain from any point to any other point, only going across sigma 3 grain boundaries. And what we found was that the GBEs under the all grain boundary condition are about double the diameter and 5 times the area, and under the excluding sigma 3 to the n, it's about triple the diameter and 15 times the area, and in both of those it's about 1.5 larger on the ASTM grain size scale. And the roll GB is slightly larger compared to the tensile GB in both, and the aspect ratio for the annealed is closer to 1, showing that they're closer to equiax. Moving on to the Vickers microhardness, slide 35, Chad. The roll GBE and the annealed are almost identical in terms of hardness, and the tensile GB is a little bit softer. This is actually pretty surprising to me given their differences in grain sizes. However, there's also a larger spread in the GBE than the annealed. So, quick summary about this. All microstructures have similar coherence to the sigma 3 grain boundaries. Both GBE microstructures have about 20% higher length fraction of CSLs, and the roll GBE is a little bit higher than tensile GBE, and the tensile GBE is also more highly deviated. The roll GBE has a higher fraction of 3 CSLs and lower of 0 CSLs. Tensile GBE has more of the 2 CSLs, but less if you're only considering the sigma 3s. And then the roll GB has a slightly larger grain size than the tensile GB. All of that indicates that the rolled GBE should be a little bit better in corrosion than the tensile GBE, based off the published literature. So moving on to the correlated corrosion in TEM. Here on the left is the SEM image of a corroded microstructure. This is exposed for 4.5 hours in a sulfuric acid bath. And on the right is the EBSD map, and the arrow here shows where we made a fib lift out. And this is just a random high angle grain boundary to serve as our control specimen. And what we found was we actually accidentally milled away our platinum coat at the top, but we still saw over 240 nanometers of corrosive attack, and neither grain is terribly close to a 111 crystal plane, being at least 11 degrees away. The enrichment of chromium is about 2% and about 0.5% in manganese, and then we depleted about 2% in nickel and 1% in iron at the grain boundary. It's a little bit hard to see in these maps, especially on the projector. But those numbers were generated by integrating a large area across the grain boundaries. So moving on, next we have the sigma 3s that I showed previously. We actually selected 3 different locations to do lift outs. The first one here is a region that didn't appear to be corroded in SEM, and in TM we can see again that it did not corrode, and we had no segregation at this grain boundary either. The surface trace is parallel to 111, currently having some issues with the ACOM indexing of the scan, but based off the Dr. Randall's methods, it's about 90% chance that it's a coherent sigma 3. When we look at one of the straight sections that did corrode, we see that we have 345 nanometers of corrosive attack, and both of the local grain boundary planes are quite far away from 111. Had, again, enrichment of chromium and depletion of iron. And then in the curved portion, again, over 20 degrees away from a 111, and 200 nanometers of corrosive attack, which you can see here. But we also see that it's not actually curved on the nanoscale. We actually have straight segments and facets. So even though it appears curved in the SEM image, it's likely structure of these very small facets. Moving on, we have a pair of sigma 9 grain boundaries. On the right, it's denoted in the blue, and then on the left, we have the zoom in of the corroded region. You can see that we have these facets here that are not corroded, then all the other ones did. So one of the corroded ones, so see we have over 400 nanometers of attack, and then both of the grains are again over 15 degrees away from a 111, and we had chromium enrichment and iron depletion. However, the sigma 9 that did not corrode was the most interesting of these, and you can see that we have this kind of faceted structure here, and a little bit difficult to see here, but there's also a grain boundary trace between, probably most likely to see it between this point here and the actual surface. So what was actually happening was the sigma 9 occurs when 2 sigma 3s meet, and then so between the left grain here and the right grain here is a sigma 9 orientation relationship, but that boundary has it appears to have dissociated into this nano twin array. So we have actually a coherent sigma 3 that we determine terminates on a within around 5 degrees away from a 111, and then we have an incoherent sigma 3 where we have enrichment of about 4% chromium and 4% nickel. This is a sigma 3 misorientation, but we don't have the grain boundary plane for that segment. Moving on, we also had a pair of sigma 7 grain boundaries. Those are shown in the yellow here, and you can see that on the left, one did not corrode and one did corrode. And they're actually separated by these 2 twin orientations on either side of the grain. So when we lifted out the one that corroded, again over 400 nanometers of corrosive attack, which you can see here, and both grains are over 20 degrees away from a 111, and we have enrichment of 4% chromium and 1% manganese, and then depletion of nickel this time instead of iron. And when we move on to the uncorroded one, you can see it's not attacked at all at that surface relative to the general surface attack. And we can see that while it's closer to a 111, it's not actually terminating on it. It's about 10 to 15 degrees away. And we actually have slightly lower levels of chromium enrichment and iron depletion. However, that variation can also be caused by potentially sample thickness and scattering in this technique. So, in summary for this section, the chromium consistently enriched at all grain boundaries except the sigma 3 coherent twins. Prior to precipitation, this indicates that precipitation hasn't happened yet. We actually have an increase in the chromium level, so it's not classically sensitized yet because we don't have the depleted region, but it would be the early stages of sensitization. However, it's still corroded, which...
Can you remind me what was the heat treatment?
Oh, For this, it was a 1 hour sensitized at 675 Celsius.
And how treated on? Did you quench or was it?
It was after the grain boundary engineering, it was quenched, and then we heated it back up to 675 for an hour.
So
Which-
some of these samples, despite being quenched,
Yes.
show segregation.
Yes. We also saw some variable depletion in iron and nickel, and then enrichment in manganese, but that did not appear as consistent. The sigma 3 and the sigma 9 that did not corrode both terminated on 111 grains, and the sigma 9 was actually that array of nanotwins. Sigma 7 that did not corrode did not terminate on a 111. However, it was significantly less deviated than the other sigma 7 from a 111 plane, and the no boundary that corroded did terminate on a 111. So moving on, Chad, slide 51, to the bulk corrosion portion. First thing we did was those images that I showed with the correlated TEM SEM and corrosion. I went through and actually counted the number of grain boundaries that were either completely uncorroded or partially corroded, meaning they had facets that were resistant, like we've been looking at in TEM, or were completely corroded. And what we found was that 90% of the sigma 3s were at least somewhat resistant, but less than 10% of the sigma 9s were. And no sigma 27 in this case resisted corrosion. Also, when we look at the total number fractions, over 50% of the grain boundaries do not at all resist corrosion. When we move on, I actually, because of some distortions and from the actual collection in our microscope, wasn't able to actually stitch the scans together, so they're just shown side by side. But what I did then was I went and colored in regions. On the left are what I'm calling cracked or arrested regions, and you can get in any individual color, you can get from one point to any other point without going over a cracked grain boundary. So those regions do have cracks going into them, but they've all arrested at some point. And on the right are twin related domains. So in this region here, you can get from any point to any other point going across a sigma 3, 9, or 27. And as you can see, they're similar, but not quite the same. Namely, on the left, the blue and the orange are the same blue on the right, and then on the right, the greenish and purple are all purple on the left. So the catch with this is that both of these extend beyond our field of view. So it's possible, and they're also three-dimensional structures. So it's possible that the CARs and TRDs are actually the same, but my experiments were unfortunately too limited to be able to determine that. Moving on to the bulk corrosion, we have the 262 practice B. This, the standard method involves immersion for 120 hours and massing it before and after to see how much mass it lost. And when we look at our unsensitized samples, so these were all quenched, but they were not heated into the sensitization range again. And you can see that we are getting attack at the grain boundaries, indicating just how aggressive this environment is. And we have our annealed, rolled, and tensile GB again, but we've also added two conditions, the annealed and rolled plus 10% elongation. And we made tensile samples from these microstructures and pulled it. And the idea is, as we're sensitizing these, we want to see the role that adding strain to the microstructures plays. So when we move, I also did the 1 hour sensitized, which you'll see the data from, but honestly, in SEM, they appear pretty much identical to the unsensitized. When we get to 10 hours, we're starting to see some differences. Primarily, we see much deeper attack, shown darker in these images, at some of the grain boundaries, and especially triple junctions in the annealed. And then, especially in the annealed plus 10% elongation, we're actually seeing grain dropout occurring. So there are just holes in the sample surface where a whole grain fell out because it corroded behind it. We're only seeing that in the annealed plus 10% elongation. When we move to the 100 hour, we can see that both the annealed and the annealed plus strain have extensive grain dropout, and in the other three microstructures, we do have some grain dropout, but it's nowhere near as extensive. This has been reported before in literature. This is one of the reasons that people have been examining the GBE microstructures, because especially under the standard test, they appear much more resistant. So when we look at this, we have the 0, 1, 10, 100 hours that I've already talked about, and we also have a 1,000 hour sensitization. So they're all at 675 Celsius. And what we can see is at the 100 hour, we have this big spike in the mass loss at the annealed, which is shown in, in the annealed plus the 10% strain, shown in the dotted line. And that's because we did start getting grain drop out there. And we also see a slight bump in the rolled GBE plus strain, which is shown by the dotted red line over the solid red line, which is just the regular rolled. So they both showed more attack, although it was a much larger increase in the annealed microstructure. When we look at the 100 hour, the strain samples are about equal with their parent microstructures again, and it's actually more clear. We can see it a little bit at the 10 hour. The 100 hour, the tensile GBE actually has significantly less mass loss than the rolled GBE, which is not what we expected based off the microstructural examination. And then things get even more interesting at 1,000 hours, because all the conditions drop in sensitization, indicating that desensitization is set in, except for the tensile GBE, which has continued to increase. Now, one of our questions is that I had was, will these twin-related domains ever drop out? So I took actually chat on slide 58, the 100 hour sensitized. There's two rolled and tensile GBE conditions that are much better than the annealed. I took those and put them back in. So this is, we're looking at sensitization time versus mass loss, and in the next one, we're looking at exposure time instead. So it's the same samples, just put back in the bath for longer, same sensitization. And what we're seeing is that our rate, which takes time into account, is actually increasing as we go to longer exposures. This indicates that we're having our grains actually dropping out faster, and we're not getting to steady state. But if you think about this, this makes sense because we haven't actually dropped out our entire surface layer of grains yet. So it's not so much that it would be immune, it's just that it would be retarding the onset of grain dropout. And one of the big notes here is that at the tensile GBE is better at all time steps, but at the 380 hours, the rolled GBE is actually the same corrosion rate as the annealed was at 120 hours. So it looks like what we're actually seeing is probably dependent on the effective grain size for dropout. And this is actually somewhat confirmed because I went fishing in our test rig for the grains that dropped out. And these are all from our grain boundary engineered samples. So actually, if I back this up to the 100 hour, you can see in the annealed, these are about 50 to 100 micron grains that dropped out. And then on slide 60, we see that these are actually 500 to 800 nanometers now dropping out of the GBE microstructure. And you can see this is actually a flat face. Almost all the grains have a very obviously flat face. So this is the polished surface of the sample, so it's still our surface layer that's dropping out. And then when we look at the 1000 hour, in the previous conditions, the polished surface looks pretty similar. It undergoes a little bit of attack, but in the 1000 hour, we actually have this very rough surface texture. And for the most, except for the tensile GBE, our mass loss went down, but we have that change indicating that something different is happening in those at this sensitization time. And this is especially noticeable in the added strain conditions, because you can see these parallel lines in some of the grains, and those appear to be the coherent annealing twins. And once we add strain and go to the very long sensitization, they're actually now being attacked, which that has not been previously observed. So the question then is, how does this fit into the published work? I'm not the first person by any means to talk about the TRD model. That was Reed and Kumar in 2006, and who actually investigated this, the corrosion with respect to TRDs in 2011. And he was the one that noted that only the sigma 3s were very, very good at arresting the cracks. All the others were at best variable. But he also noted the corrosion pathways between his TRDs. So in the left, see he has these C numbers. This is slide 62, Chad. And each of these C numbers indicates a twin-related domain, and there's a Heingel grain boundary path that goes around each of those. Then when he looked at the corroded samples, these are actually cross sections. So the corroded, the original sample surface is up here, and you can see that it's corroded 200 nanometers and 200 microns and 900 microns in this case. In the annealed specimens on the left, and in the GBE specimens on the right, it's significantly reduced. And when he plotted the mass loss, he was actually looking at three different conditions with different levels of CSLs. And the two lower conditions, you can see this rapid increase in the mass loss rate around 12 hours. However, the specimen A with 73% CSLs see a much, much lower increase in the mass loss rate. And he attributed this to the TRDs.
Total mass loss is not rate.
Sorry, yes. He was reporting total mass loss. This was actually a slightly different environment as well. It wasn't the standard ASTM 262. But what he was hypothesizing was that the surface layer of the TRDs is protecting the lower TRDs. Since they're relatively large, it would he hypothesized that it would take longer for the a lot longer actually for the cracks to get around behind them and expose the grain boundaries underneath. However, this is directly contradicted by what I've observed in the extended mass loss testing, and because I'm noting a rapid increase in the mass loss as soon as you start dropping TRDs. So finally, we have our bulk corrosion with the U-bend specimens. This is for testing intergranular stress corrosion cracking. We actually ended up using three different procedures on the same set of specimens. First is the ASTM G123, which is a standard solution of sodium chloride spiked with phosphoric acid that boils about 110 Celsius. And the standard the test is specified to go up to 1,000 hours, and in their interlaboratory testing, every single specimen of 304 and 316 that they tested failed, mostly within 48 hours and all within 2 weeks. And 1,000 hours is right around 4 weeks. What I found though after that testing in the top row is not a single one of our specimens showed any cracks at all. So we went back and we did the G36 test, and that's magnesium chloride. It's known to be much more aggressive, but we did it at 110 Celsius, which is has been shown to promote the corrosion cracking. And after 2 weeks, we still had no cracking. Finally, we went for the full G36 at 155 Celsius, and within 24 hours, every single specimen cracked, and they appeared to be mixed mode intergranular and transgranular. So unfortunately, from that, we couldn't say much about how microstructure actually affects it because they all crack at the same time, appear the same, especially with transgranular cracking. However, interesting note from that is that relatively modest nickel content in 316L massively increased the stress corrosion cracking resistance, which was not expected. So our conclusions. We developed the method and code to calculate grain boundary plane using the ACOM scans. We developed through thickness grain boundary engineering using the iterative method. Showed that it does propagate to the center of half-inch bars. And then we did TM examination of uncoded grain boundaries. Saw that sigma 9 terminating 111 associated in sigma 3s and did not sigma 3s corroded, did not terminate on 1s, sigma 7s pair did not share the same grain boundary plane. The rolled GB microstructure appears more corrosion resistant than the conventional criteria. It's got larger length fraction every criteria. It's got less deviation from ideal sigma 3, more of the sigma 3 junctions, grain size, and similar sigma 3 color microstructures. The A262 practice B shows that tensile GB has lower mass loss. Every condition except for that 1,000-hour sensitization, where we saw the change in the surface texture as well. Our curved sigma 3 grain boundary still resisted cracking. Basically, you end up with facets that do not corrode. And about half of the sigma 3 grain boundaries encountered with corroded uncorroded facets. The crack arrest are more similar in size to twin-related domains. They weren't identical in this work, but were limited by our field of view using the technique that we did. And extended mass loss testing shows that the mass loss has not reached steady state yet. However, we did reach the same mass loss after 380 hours. Mass loss rate after 380 hours in the GB microstructures that we got in the NEALD after standard 120 hours. Our grain size for dropout was also 500 microns for the GBE, and this is likely to domains or crack arrests are dropping out. We noted our strain increase sensitization and desensitization rate, both in the NEALD and the rolled GB. But the rolled GB was more resistant. At 1,000 hours, we saw that the tensile GB conversion rate had continued to increase at decreasing like the others. We had the change in surface roughness. Strain started causing the sigma 3s to corrode. Also raising the nickel content 316L. Greatly increased the IGSCC resistance. And finally, circling back to the questions that we had earlier. Does the grain boundary play a role in the corrosion resistance of grain boundary steel? Yes. It's for each individual grain boundary segment. As they curve or facet, everyone has a different grain boundary plane will have different corrosion resistance. How do corrosion resistant grain boundaries affect both corrosion resistance material resistant segments arrest cracks. So in the TRDs you actually end up with crack arrest and they drop out as whole units. And then the question that I didn't know that I should have asked was what role do twin-related domains play? And from this work, it looks like the crack arrest region or TRD size most likely the most important factor in the inter-granular corrosion of these microstructures. And final technical note, it really is a lot easier to study IGSCC and will actually undergo IGSCC. So for future work, really what needs to happen is better analysis of twin-related domains as well as the crack arrested regions. To study how the TRDs form and size. This is going to be especially challenging given their size and the fact that they're three-dimensional. So your twin chains can actually be going up or down in addition to it round. And we need to be doing long-term corrosion studies to